Okay, so we're done with chapters 1, 2, 3, 4, 5, and 6. And we're starting chapter 8. And just as a reminder, we've kind of gone through a couple different things. But they all have kind of covered the same sort of idea. Chapter 2 and 5 was the kinematics. Chapters 3, 4, 6 have been kinetics. And really, all we've cared about is really looking at acceleration and velocity in chapters 2 and 5. Second law, which is really the only thing we study in this course, is various forms of second law. But remember that we are limited to motion in the xy plane. And I'm going to make my life a little bit easier and not write every possible form of this. Instantaneous solutions for 3a, 4.2, 6a. And then force, velocity, and distance when dealing with, with energy. So in the end, you ended up with mv squared over 2 here, and ig omega squared over 2 for those terms. For 3c, we started to look at momentum, and momentum in that case, m dv dt, or ig omega. But the goal you have in the next 2.5 weeks, 3 weeks, is to sort of identify what these problems are. So you have a lot of resources available on Quarkus, past exams, all the information you could possibly want. Please spend the time not just looking at the solutions, but doing the problems. So where we're going to go today is chapter 8, which is vibrations. And often when you think about vibrations, you sort of say, well, this has nothing to do with anything I've done up till now. But really, it is an expression of this form of the second law. Sum of forces equals mx double dot. And we are going to write a set of differential equations, ordinary differential equations, for these particular cases. And so one of the things you should be thinking about as you're going through this entire chapter is that this is not an analytical chapter. This is a recipe book. You need to understand what the solution looks like, and you need to set everything up properly at the beginning. So I will write that down. You probably won't believe me, but this is really just a cookbook. All right, so here I have the typical problem we start with. And this is a case where I have a mass and a spring, and the spring has a spring constant of K. And I need to sort of start looking at what happens. So it displaces a distance x, and this is the location of relaxed spring. So if I look at this right here, I have weight acting downwards, I have the normal force acting upwards, and I have a kx. And kx is just the force that comes from the spring because it wants to pull it back to the left. I've stretched it, it wants to push back. And my governing equation is going to look like this. And in this particular case, I don't worry too much about what's happening in the y direction, which I should define x and y. But I can see that the force x is a negative and mx double dot. And one of the things that you'll notice as I go through all of these solutions, I am going to end up writing the equations in a certain form with the same sign in front of each of the terms. So I didn't do this as a compression. If I'd done it as a compression, kx would be pointing outward, it would be positive, and my kx would be different. But I want to write this in a particular form, and I end up with mx double dot plus kx is equal to 0. And I can write that as x double dot plus k over mx, which equals 0. And I end up with this term right here. And I'm going to define omega n squared as k over m. So I need to be able to recognize what my terms are out of an equation that is going to look exactly the same no matter how many different ways I write it. So omega n, which is the natural circular frequency, and I'll go into more details in a few minutes, has the form square root k over m. So it's the spring constant over the mass. Now, I messed up with the distances. So my solution in this particular case, it's a second order term. There's no first order term. So if I have a solution for x, it can be something that is going to have the same form as x and x double dot. And what's nice is a sine and a cosine. So x is equal to a cos omega nt plus b sine omega nt. I can also rewrite this as c times sine of omega nt plus a psi, just a phase lag. And all I need to do in order to solve for these problems at this point is to write out what the solution to the problem are based on finding A, B, or C and psi. And that's going to be based on initial displacement, x equals x naught, initial velocity, x dot equals x dot naught, and then I substitute and solve. at t equals 0. So say, for example, I did give you those values. In that case, x is equal, or x naught is equal to a, and b omega n equals x dot naught. And my function for the first form of the equation is just going to be x equals x naught cos omega n t plus x dot naught divided by omega naught, or omega n, sine omega n t. So from that to that. So, if I want to go another way and solve for c and psi, here is a and b, then what I'll do is x naught equals c sine psi, x dot naught equals c omega n cos of psi. C is equal to x naught squared plus x dot naught omega n squared over square root, and psi is equal to a mess tan inverse x naught omega n over x dot naught. Okay, that's a mess. In all of these cases, all you're trying to do is just substitute in terms. So you take your top equation, you take the derivative of it. When you take the derivative, you then use your initial conditions, x equals x naught, x dot equals x naught dot, at time equals 0. And from that, you can calculate either a and b or c and psi. If you do this, you end up with x is equal to a mess, x naught squared plus x naught dot omega n there we go, sine of omega nt plus inverse tan x naught omega n divided by x naught dot, and that mess is the same thing. Now, both of these equations, which are sort of now completely kind of unreadable, are exactly the same result. So the first form of the equation where you solve for a and b actually is a lot easier because you don't have to sort of mess around with a combination term, but both of these give you the same result. Which is why I wanted to sort of scramble to this. So if you look at what that looks like, it's kind of a circular sort of solution. It's a sine wave that is phase lagged, so it doesn't go to 0 at x equals 0, but it has a value y naught or x naught as it starts, because remember this is one-dimensional motion, so I'm just solving for x naught. My A and B define where those terms are, so if I want to use that approach, or C, which is essentially the right triangle, or the hypotenuse of the right triangle made of A and B with an angle psi in between it. Now, the motion you can see is a sine wave, and as a sine wave, it never diminishes. Now, that expertly drawn by hand sine wave is not meant to be absolutely correct. It's just supposed to give you a sine wave-ish looking thing. But the period between the two peaks is defined as tau, which allows me to define a couple things. So I have the natural circular frequency I have the natural frequency and the period of the cycle. So, in terms of values, the first one is the one we just derived, omega, which is equal to square root of k over m. And it has units of rads per second. And one of the things that I'm going to recommend that as you solve all of these problems, you recognize immediately that rad over seconds is the same as 1 over seconds in terms of notation, but keep the rad. It actually helps you as you're going through very complex calculations to realize when you're dealing with rotational motion. And it represents the rate that that vector c rotates around that unit circle. So I've defined a circle here. I've got a radius, or it goes out, well, it's not quite yet. This is not to the circle. This is the radius. It goes out to there, and c is going to essentially go up and down. So as it goes up and down, I can sort of put it on a unit circle and define it that way. If I look at natural frequency, that is equal to omega n divided by 2 pi, and it has units of hertz, or Hz. And that represents complete cycles per unit time. So the rate, the frequency of c is omega n. The number of peaks to troughs back to peak is going to be the natural frequency. Finally, there's the period. And that has units of seconds. And that's the time for one complete rotation of that constant c. So it's going to go round and round and around. And there you go. One of the things you have to know, and again, this is stuff that I think is on various crib sheets that we give you, but this is stuff you need for the final, because we can ask you for natural circular frequency. We can ask you for natural frequency. We don't have to tell you during the exam what that is. We expect you to know. I gave more room for the spring. I can do the same thing, but with another orientation. So I have a mass and a spring again, but now the spring is vertical. And because the spring is vertical, the spring will have a relaxed length that's defined here. When I slowly attach and allow slowly for the mass to drop, I will have a static deflection, which is defined by delta m. I will keep using x because a lot of what we're doing in this course, in fact all of it, for vibration is single dimensional. I should have put two together. And again, as much as possible, draw. Put down your free body diagram. So the first thing I'm going to do is I'm going to look at the static case where it's just deflected, and I have x and I have delta m. So the spring has displaced a distance delta m. I know, or I'm told, what the spring constant is, and so in that case it's just k delta m and mg. If I go to the deflecting case, and maybe not that. I rotate this around, I got x and y in this direction, so it makes my life easier. I have the deflection of the spring from the point of where I released it. So I displace it a small amount, and then it's going to start vibrating. So it'll move back and forth. It never stops. At this point, there's nothing to damp out motion. And so if nothing can damp out motion, the solutions that you see are always going to be nicely repeatable. So for equilibrium, I can say that mg minus k delta static, I should have used, oh no, that's right. Is equal to 0. So all I'm saying there is that for the equilibrium case, where it's just in balance, and I have defined positive as downward, mg minus k delta m is equal to 0. So one of the differences with this orientation is that I do have to worry about the mass. So and however I've defined x in this particular case, I can rewrite it, and usually I will rewrite it, so it's mg minus k delta m plus x equals mx double dot. Now that leads to sort of the interesting result that these two terms here are these two terms here. So these go away. I also have a really nice result because one of the things I need is a form of the equation that makes sense, so I've displaced it in such a way that it works. I have minus kx, which is equal to mx double dot. Maybe I'll say kx total there. And you'll notice immediately that I have defined my system in such a way that I can bring this term over to this side, and I get the exact same equation as I got at the beginning of the lecture. Yeah, right there. That's not accidental. The form of the solutions that you're going to get are all going to have positive coefficients for all of the terms. So the goal here is to write everything out in the same form and solve it the same way. So there's not much to this, but you do have to do them a few times to convince yourself that it's worth a lot of effort to sort of understand them. Now, one of the things that I have found over the years, and if you're looking for a summary video to watch, there's a summary video on series and parallel springs. And you've done a lot already in ECE looking at series and parallel circuits. This is very similar. So here I have two springs. They have a constant which is given as K1 and K2. And they're connected in series and parallel to block A. And block A is this thing right here, has a mass M. And are connected in series to block A, vibrates in simple harmonic motion with a period of 4.5 seconds. When the blocks are connected in parallel to the same, oops, that's not what I wanted. Oh, there we go. When the two, are connected in series to block A and vibrates in simple harmonic motion with a period of 4.5 seconds. When the two springs are connected in parallel in the same block, the block vibrates with a period of 1.7 seconds. So here they have a period of 4.5 seconds, and here they have a period of 1.7 seconds. So tau in series, 1.7 seconds, tau in parallel, 4.5 seconds. Actually, I'm not going to do that right away. So let's start with this. And I have, in this case, I have K2 delta static, K1 delta static, and I have a pulling force. And if I look at that, that pulling force is going to be the same. It'll be K1 delta static plus K2 delta static. And one of the things that I know, go ahead.
In the pump of the question, it says that it vibrates for a period of 1.7 seconds when they're in parallel, but you wrote it for series.
Oh, that's all right. There you go. So I have both of these undergoing the same force. And what I know is that I can find a K equivalent that has the same displacement as K1 delta static plus K2 delta static. And if that's the case, it's going to be P over delta static equals K1 force over all of them is going to be the same, so it'll be K equivalent delta static equals K1 delta static plus K2 delta static. And in that case, K equivalent for the parallel case is K1 plus K2. You're going to go through a lot of different cases looking at parallel and series cases. But the force in the springs has to be the same. Now, if you do similar sorts of things with series, you know that the delta of the springs in both cases have to be the same because you can't have it sort of twisted. But in series, the force has to be the same too. So in that case, you end up with a relationship which is Ks in series is K1, K2, all over K1 plus K2. So now you have series relationships and parallel relationships, and you're going to find yourself doing different cases where you have to sort of do the equivalence, and maybe not call it K equivalent, just call it Kp for the two cases. Okay. You know what the... Oh, how did I know that? So why did I go through all of this trouble to make an equivalent spring constant? Good question. So what's the answer? The answer is I want to go back and create my spring mass system. Because for the spring mass system, I'm going to end up writing mx double dot plus ksx and kpx is equal to 0. Those will be the equivalent terms that I'm looking at here. I didn't do my first example. So if I do that, and I just sort of put everything together, I have tau s over tau p, and I square them, it's equal to 4.5 over 1.7, which equals kp over ks, which equals K1 plus K2 all over K1, K2 over K1 plus K2. So the ratio between the two ends up being 7 K1, K2, which equals K1 squared plus twice K1, K2 plus K2 squared. So I'm adding all the terms up, and all I'm trying to do in this particular case, in this mess of an equation, is to come up with the same form of the equation that I've written. So I want to have mx double dot plus kx is equal to 0. And once I do that, I recognize then that I have the natural frequency, I have the natural circular frequency, and I have the period. What's the question?
So when they're in parallel, right?
Yes.
If they have different spring constants, in order for the force to be the same, the deflection will be different, right? The stretch or the delta.
No, so we assume that the deflection is the same in parallel.
Okay.
The series, the force is the same.
In series, the force is the same, but in parallel, the deflection is the same, but the force will be different.
That's right. Because they have to hold each other.
Yeah.
So if I had deflection, sort of consistent deflection, then what would happen is I'd have a moment associated with the mass.
Yeah.
Okay? So once I have all of this, I have an equation, everything works out really nicely. I end up with k1 squared minus 5k1 k2 plus k2 squared equals 0. And I get k1 equal over k2, which is equal to, I'm going to go just with the partial one, square root of 21 over 2, or k1 over k2 is a ratio of 0.21, or 4.79. You can solve through for all of this, but ultimately, the cheaty bit here is that once I have it in this form right here, I can solve the whole thing. Once I solve the whole thing, I'm done. I just am looking to set up the equation in one form, mx double dot plus kx, and never ever have a negative term in that equation. Good? All right. Let's try another example. Go ahead. Oh, I did do that. Oh, good for me. Oh, why don't I derive the one for the series? So I have K1 and K2. In the series case, the force anywhere through the system has to be the same. So the force is equal to K1 delta 1. Force is equal to K2 delta 2. That doesn't mean that delta 1 and delta 2 are the same. It just means delta 1 and delta 2 are going to sort of play a role in determining what my final result is. So delta 1 plus delta 2 is equal to delta. And I can write each of those as force over K1, force over K2 is equal to force over K equivalent. So force over K equivalent. Rearranging terms, I can write 1 over K1 plus 1 over K2 equals 1 over K equivalent. And I end up with K equivalent equal to K1, K2 over K1 plus K2. Okay. And again, only thing you're trying to do here is to make a substitution, have from that substitution an equivalent that you can then put into your standard form of the equation. And once you have it in the standard form of the equation, solve for it. Go ahead.
So I put like a bit before when you got to the solution for
Yeah.
the previous problem, can you like kind of go through how you got there from, because you went from the k1 squared one to the
Yeah, so I divide out by k2.
right out of the
Yeah, divide by k2. I can rewrite everything and solve through. Okay. I didn't want to go through the mechanics of that. Do I want to say anything else? Okay, I think I'll leave it at that. I mean, again, there's a nice summary video I did a while ago that looked at particularly this case. Did I do this example already? Oh no, I have not. All right. So this is probably the last one. My interest in series and parallel springs is because it ends up being a source of great confusion. So I have a block of mass 50 kilos which moves vertically. I have K1 and K2 again. In this case, K1, K2, K1, K2. The block is pulled down by a distance of 40 millimeters and released. K1 is 4 kilonewtons per meter, 6 kilonewtons per meter for K2. Find tau, max velocity, and max acceleration of the block. And again, you're just setting this up as a recipe. You're just going through and solving through for everything in the same form. So for the parallel case, you have a force down. You can say P equals K1 delta ST plus K2 delta ST. K is equal to P divided by delta, which is equal to K1 plus K2. And the K equilibrium in this case is 10 kilonewtons per meter. And so what I get out of that now is gold, my K equivalent, and my X displacement. So from that, I can write mx double dot plus omega n squared, x is equal to 0. And you'll notice that I didn't even bother doing anything because once I've written it in this form, I've already solved the problem. So you're writing out a free body diagram, you're writing out all of these terms, and you're solving through for that. Now, because I'm extraordinarily careful with my units, I recognize that I have a spring constant in kilonewtons, and so I'll have 10,000 newtons, not 10 newtons. So putting the terms in, 14.14 rads per second. Now everything else is straightforward definition. And then you can just substitute directly in. So you know what omega n is. You're going to just set t is equal to 0 or maximum value. And from that, you can just calculate where you're going to go with that. Hmm?
And this x dot, what does that say? C omega sub n, what?
Yeah, omega n, cos,
Cosine of omega n
t plus
t
I.
plus psi. And then the original equation, the first one,
Yes,
why did we write omega n squared x instead of kx?
because that's the definition here. Remember that k over m, if I substitute, or actually that shouldn't be there. There you go. Better? So the max velocity is going to be Vmax, which is equal to c omega n, which is 0.566 meters per second. Amax is equal to c omega n squared, which is 8 meters per second squared. All right, really quickly, I don't need to go through this for part B. I can just say that K equivalent is equal to K1, K2 over K1 plus K2. Again, all I'm doing is taking this case where I have x displacement and now I have K1, K2, and I'm substituting it in for this case where I have the mass and I have Kx equivalent over x displacement. You'll also notice that I have not worried at all about the weight because the weight disappears in the static term. Once you do that, omega n is equal to square root of k over m, which is 6.93 rads per second. Tau n is equal to 2 pi over omega n and 0.907 seconds. Vmax is the same, Amax is the same. It's c omega n squared and c omega n. The omega n's have changed. 7 meters per second, 1.92 meters per second. So a much lower acceleration and velocity for the series case, despite the fact that you are, dealing with the same system in the sense that you have the same springs, differently oriented, and the same mass. So the whole system sort of does that, gets 0.277. And you'll notice I'm not really doing any type of analysis. I'm putting in all of the free body diagrams and just putting in the results. So once I have this, I can write that. I don't even have to write mx double dot plus kx or minus kx is equal to 0, or mx double dot, no, it's plus kx, or minus kx, that's right. So I have the downward direction as positive x. But in the end, all I'm going to do is just write omega n equals square root of k over n. You're going to find this helpful if you spend a little time on it and just go through a couple cases. Next week, what I will be doing is starting to look at rigid bodies. We have a total of 6 lectures on this. And then there's the last lecture, so we are coming quickly to the end of the course. Thank you very much. Oh, no.